So, good day everyone. For today's video, we will be talking about partial ordering. So, I am Justin Clyde M. Anunas from BS Statistics 1-B of CTU Main Campus. So, first, let's talk about ordering. So, ordering can be written as n is less than or equal to m if there exists k is an element of zero and natural numbers, such that m is equal to n plus k. And we can write n is less than m if n is less than or m and n is not equal to m. So ordering has three properties. First is the reflexive. An element is related to itself. Second is the antisymmetric. If n is less than or equal to m and m is less than or equal to n, then n is equal to m. And the transitive property. If n is less than or equal to L and L is less than or equal to M, then we can say that n is less than or equal to M. So, to prove the transitive property, assume both statements in C are true. So, there exists k sub 1, which is an element of 0, a natural number, such that L is n is equals to n plus k sub 1. And there exists k sub 2, which is an element of 0, a natural number, such that m is equals to L plus k sub 2. Since we need to assume that the both statements in the C are true. So, therefore, we can say that m is equals to L plus k sub 2. Then, since L is equals to n plus k sub 1, we substituted the n plus k sub 1 here. So, you can say that m is equals to n plus k sub 1 plus k sub 2. Then, regroup. So, we can say a k sub 1 plus k sub 2 here, which maps the k that is an element of 0 and natural numbers. So, we can say that n plus k is equals to m. Therefore, there exists k which is an element of n sub 0 such that m is equals to n plus k is true. So we can say that n is less than or equal to m is true. So what is a partial ordering? Let's say we have a relation R on a set S. A relation R is called partial ordering or partial order if it is reflexive, antisymmetric, and transitive. So, a set S together with the relation R is called partially ordered set, where n is related to m. Example, show that the relation R, which is equals to n comma m, such that n is related to m, defined on set S is equals to 1, 2, 3, 4, 5. So relation R is said to be partial ordering if R is reflexive, antisymmetric, and transitive. So the reflexivity, so we can say that it is true. The n is less than or equal to n is true in the set S, which is equals to 1, 2, 3, 4, 5. And the antisymmetry, the relation n comma m. So we can also say that it is true because if n is less than or equal to m and m is less than or equal to n, then n is equals to m. Then the transitivity, if n is less than or equal to L and L is less than or equal to m, then we can say that n is less than or equal to m. So, it is true. and say that the relation R is reflexive, antisymmetric, and transitive. Therefore, the R is a partial order relation. But what is the partial in partial ordering? The word partial in partial ordering indicates that not every pair of element in a set is comparable. So, to differentiate what is comparable and incomparable, when we say comparable, the element n and m of partial ordered set are called comparable if either n is related to m or m is related to n. And we can say it is incomparable if the element n and m of partial ordered sets are called incomparable if neither n is related to m nor m is related to n. Remember, we can use S, relation to represent an arbitrary partial ordered set where n is related to m is used to denote n, m, which are element of R. So to show what is the difference between incomparable and comparable, here is an example. So we let n equals to the power of s, and m is a subset of s. And where s is equals to 1, 2, 3. In the partial ordered set, power of s and subset of s, if n is 1, 2, and m is 3 is a set containing 3, these two sets are incomparable since n is not a subset of m and m is not a subset of n. On the other hand, if n is a set that contains 1 and 2 and m is a set that contains 1, then we can say that 1 is a subset of 1 of a the set that contains 1 is a subset of the set that contains 1 and 2, which makes it a comparable one. So that's all for today's video, and I hope you learned something. Bye!